Hi everyone, in today's class we are going to discuss about inductance. So inductance is nothing but a wire of length L. When it is wounded with n number of turns, then it is called as an inductor. For every conductor, it is carrying a current I and producing magnetic flux B, and there exists a self-inductance. When two such coils are placed very close to each other, then it is called as mutual inductance. First, we are going to derive the value for inductance of a solenoid. So the notation for calculating inductance is L, and the formula for inductance is given by L is equal to N phi by I, where N represents the number of turns, phi is the flux, and I is the current. First, we are going to find out the value of inductance of a solenoid. So for that, we are just considering a solenoid with n number of turns. Then current I is the flowing through the solenoid. Let L be the length of the solenoid and A be the area of the solenoid. So we know that already we have discussed that the magnetic field intensity at any point on the solenoid is given by H is equal to Ni by L. The total flux linkage is given by N phi is equal to N phi. So in the phi, we can instead of phi, we can write phi is equal to B into A, where B is the magnetic flux density and A is the area of cross section. So from equation 1, it is clear that B is equal to mu Ni by L. Now what we are going to do is we are going to substitute the value of B in equation 2, and therefore N phi is equal to mu N square, N into N, it will become N square Ia divided by L. The total flux linkage is given by N phi is equal to mu N square Ia by L. So as we discussed earlier, L is equal to N phi by I. So now we have calculated what is the total flux linkage N phi. So we know the value of current I. So now what you are going to do is we are going to substitute the value of total flux linkage and current in that above equation. We get L is equal to mu N square A by L, from which we can say L is directly proportional to N square A by L. So that from that you can confirm that when the length of the solenoid is too high, the inductance becomes very small and it doesn't depend upon the current I. That is the conclusion. Next, what we are going to do is we are going to calculate the value of inductance of a toroidal ring. Toroidal ring is nothing but it is the same as that of solenoid, except that solenoid is a straight wire. It is like a straight wire, whereas this toroidal ring, the same in solenoid, when it is rotated, when it is formed like in a circular manner, it becomes a toroidal ring. And this toroidal ring, it carries a current I inside it, and therefore the flux will flow through that coil, the ring. So the radius is given by R. So now we have calculated we know that the value of H for a toroidal ring is given by H is equal to Ni divided by 2 pi R, because it represents the circumference of the circle. So now first what our aim is to find out the total flux linkage, and then we have to substitute the values. The total flux linkage is given by N phi. So instead of phi, I can put BA. So therefore N phi is equal to N into B into A. Now we have to calculate B. B is equal to mu H. So now instead of H, we have found out H from equation 1. H is equal to Ni divided by 2 pi R, and therefore B is equal to mu Ni divided by 2 pi R. Now we are going to substitute the value of B in equation 2. So when we substitute that, N phi is equal to N into B. Instead of B, I can write mu Ni divided by 2 pi R into A. So now I can write the total flux linkage is mu N square Ia divided by 2 pi R. So as we know, the formula to calculate inductance is L is equal to the total flux linkage by current. So we have found out the total flux linkage N phi. Substituting the values, we get I in the numerator and denominator get cancelled. Therefore, L is equal to mu N square A divided by 2 pi R. So this is the inductance of a toroidal ring. From this, we can come to a conclusion. L is directly proportional to N square A divided by R. So from this also we can conclude that it is confirmed that it depends upon the number of turns and the area of cross section. It doesn't depend upon the current. That is the special feature of this inductance. Now the next what we are going to see is we are going to calculate the inductance of a coaxial cable. So already we have calculated the value of coaxial cable, H vector. So H vector is, for a coaxial cable is given by H is equal to I divided by 2 pi r. So the total flux linkage is N phi. N phi is equal to N into B into A. So instead of B I can write mu H. So that I am writing. So instead of H I've got the value H is equal to I divided by 2 pi r. Substituting the value we get N phi is equal to mu N I A divided by 2 pi r. The total flux linkage N phi is equal to mu N I A divided by 2 pi r. As we know the formula to calculate inductance, L is equal to N phi by I. So we have calculated N phi, substituting the value of N phi and I. So I get cancelled, leaving out L is equal to mu N A divided by 2 pi R. The same value we can just write for if it is calculated for the distance d, then L by d is equal to mu Na divided by 2 pi r. So from which you can come to a conclusion L is directly proportional to Na divided by r. So that means the inductance, it depends upon the number of turns and area of the cross section and the radius r. So this is about the inductance of a coaxial cable. So far we have calculated the inductance value for solenoid, toroidal ring and coaxial cable. So another important topic in magnetostatics, the energy storage. Now we are just considering the energy storage, for which we are considering a rectangular system, rectangular plane, where we have a conducting sheet 1 and 2 placed on the plane. So as we know earlier, the energy stored in the inductance for the magnetic field is given by Wm is equal to half into Li square. So the differential energy is taken, so the above equation will change as del Wm is equal to half del L del I square. First we have to find out the value of del L and then we have to find out the del I, so that we can get what is del Wm. So del L is equal to L, we know that L is equal to phi by I. So then del L is equal to del phi by del I. Keep that equation as number 3. We know the relation as we discussed before. The relation between flux and flux density is given by surface integral B dot n cap ds is equal to phi. Therefore del phi is equal to B into this surface integral ds will change as del s. So now we have got the value of del phi, we have got the value of del L. So now what we are going to do is we are going to substitute the value of del phi in equation 3. So when you substitute the equation, the value of del phi in equation 3, we get del L is equal to B into del S by del I. So we know that B is equal to mu into H. So therefore del L is equal to mu H del S divided by del I. Here the surface, it depends upon, it is lying on the x and z plane. Therefore del S is equal to del x into del z. Therefore del L is equal to mu H. Instead of del S I am replacing that by del x del z divided by del I. Next our aim is to find out the value of del I. So as we know by Ampere's circuitous law, line integral H dot dl is equal to I. So instead of this dl I can replace that by del L. H dot del L is equal to I. Here it is lying on the y plane, therefore H dot del y is equal to I. So from that I can write the equation number 5. Del I is equal to H into del y. So now we have got the value for del I. So what we are going to do is we are going to substitute the value of del I in equation number 4, that is del L, and therefore del L is equal to mu H del x del z divided by, instead of del I am replacing that by H into del y. H and H get cancelled, therefore leaving out del L is equal to mu del x del z divided by del y. Keep that equation as number 6. So now what we are going to do is we are going to substitute the value of del L and del I in equation number 2. Therefore we get del Wm is equal to mu into del x del z divided by del y into H square del y square, that is I square del I square. So we can just cancel the del y term and we get del Wm is equal to 1 by 2 mu H square del x del y del z. We know that del x del y del z is nothing but it depends upon the volume, and therefore that can be replaced by del v. Therefore we get the simplified term as del Wm is equal to 1 by 2 mu H square into del v. Next our aim is to find out the value of Wm. So when we want to find out the value of Wm, we know the formula, limit del v tends to 0, del Wm divided by del v. So we also know that Wm is equal to half into mu h square. So the half mu into h square can be that can be expanded as half mu h into h. Instead of this mu h, I can replace that by b, and instead of this that is Wm is equal to half into b into h. So now what we are doing is we are just writing in terms of mu. So mu get cancelled, leaving out Wm is equal to 1 by 2 b square divided by mu. Keep this equation as number 9. These equations 7, 8 and 9, they are representing the expression for energy storage in magnetic field. That is in 3 different ways. But all the 3 represents the energy storage in magnetic field. With this we are completing the magnetostatics. Thank you.